I wasn't able to show myself as a medical excuse.
Oh, yeah. All right, so, before I start, any questions on what we've covered? By the way, the solution should be up on OneNote. Did you see them? Anybody see them? You saw them? Okay. I'm just making sure they're there. I put them up, and honestly, sometimes I don't know if it updates or not, because I'm doing this at home. All right, well, we're into chapter 4. We're going to go through this section, up through section 4.4, and if we have time, we'll get the students' T distribution. Then we're into the next couple of chapters, and we're going to be talking about spectral energy density, or really autocorrelation related to power spectral density, and a few other things that are pretty important. Okay. So, let's see. This is just part of the deal. What I wanted to do, I think the best way to see most of the ideas behind these formulas and stuff, or how to apply them, is just by doing problems. So what I want to do, I want to put a few things up, a few notes up on the board that we're going to reference, and then I'm going to apply to some example problems, one example problem in particular, and then to problems in the back. Now, so far in the sections in chapter 4, what we've covered is that the variance of the mean of the sample, and that's the indication for the sample mean, would be equal to sigma squared over n, and this n is the sample size. N would be the sample size. If n is much less than capital N, where capital N would be the actual number of the number in the actual population. And then, remember, these are the two things from section 4-2. The variance of x bar hat would be equal to sigma squared over n, and it would be then n minus small n over capital N minus 1. Capital N, of course, is the population size, small n is the sample size. Everybody remember these things? Now, you're going to have to know this. I'm going to just tell you straight up. This is from section 3.2. With me? Most of the problems have to deal with how many samples do you need to take if, and they'll say something like the standard deviation is 1% of the variance, something to that nature, and you have to take the words and fashion it into the problem statement. How many have tried these problems, right? They're fairly straightforward if you understand how to translate the wording into the problems, the actual formulas applied. Everybody with me on this class? Now the next part is a little different. Now we talk about the samples, and this is going to be the sample variance. And the sample variance is S squared bar in the book. Now, here's some key things. Everybody follow me on this? This is the samples variance. If you want the mathematics for that, it's pretty straightforward, because a variance in any case is going to be the expected value, and this would be of the samples of x of I minus x of I, and it would be that squared. So it's the expected value. If you have the sample's mean, then you can subtract that from the value of each sample and square it, and if you sum that whole thing, you get the variance. Do y'all follow me in this class? It's straightforward if you think about it. They have this, but the expected value of just the sample's variance is actually equal to, remember this, it's going to be n minus 1 over n, wait a second. I think this is the way he does this in our book. he has it.
For the S squared formula, he has 1 over n in front of the expected value.
Well, there's two. There's the unbiased and biased. I gotta make sure with the symbolisms. For the biased estimate has n minus 1 over n. If you look at that, you see it? He'll say bias estimate is n minus 1 over n right here times sigma squared. You see that? It's called bias estimate. Then there's the unbiased. What I want to make sure is he has thus the bias estimate right there. This is the unbiased. I'm about to get to that. Now, when you take a look at this, is called the bias estimate. You remember the statement I made up front? We were talking about this. This is the reason I call it biased is this. Look, you would expect. Remember from before, if you take a look at the expected value of the sample's mean, right? That is x bar. So the expected value of the sample's mean is the mean. Follow me? Because that is a statistical, the sample, when they talk about the sample's mean, they're saying it's a random variable as well, because every time you grab a new set of samples, you got different values. So you would expect, at least it would make logical sense, that the actual expected value of the sample's variance would be the variance, but it's not. So they talk about the unbiased value, I'll put it here. What it's going to be is the expected value, and it depends how you want to do this, but if I just put s squared tilde, something to indicate this is going to be unbiased, it's equal to the inverse of this, n over n minus 1 of that, the expected value of the actual variance. And the reason I'm doing this is the one we use almost all the time. And the reason is also because this itself will be equal to sigma squared. Did you see that in the problem? Right? I'm sure he has this in that section, right? He's going to have the unbiased estimate, and he'll have a symbol. He has like a tilde. You see that? So I try to make it clear. This is an unbiased estimate. These are all about the variance, but now here's where it gets really interesting. Now we're going to talk about the variance of the variance. I want to just take a moment here, and I've got to make sure, if you haven't been reading this and keeping up, you need to get onto it right now, because this gets confusing in a hurry. And if you just try to do it like on a Thursday night for a Friday quiz, I think you're really going to be hurt. You can get really confused with this stuff. And the way he does it, at least in my opinion, is not as crystal clear as it could be. So right now we're talking about a sample in the variance, right? Everybody understands the variance would be basically really this, right? That would be the variance of the sample. Now, in order to get the variance of the sample, the expected value of the variance of the sample to equal sigma squared, that's what you'd like. Now you have to multiply it by n over n minus 1. Now if n is large, 100, 150, 200, it's pretty much the same. But if n is small, like 3, 5, 10, then it's not. Y'all follow me on this class? And this becomes important later. So now we talk about the variance of the sample. And if this, I'm going to put the biased one up there. And if I put s squared bar here, the variance of the sample is going to be equal to u to the 4th, which I'll explain, minus sigma to the 4th over n. And this is biased. So this means we're using the definition of the variance that is biased. Back there. Y'all with me, class? Now, if we go ahead and we want the unbiased, and this is the thing I'd recommend we always use, but in the book he doesn't state it that way. The variance of the unbiased, and I'll put a tilde or something there, squared bar, is going to be equal to, and the way he does it, he's going to have n over n minus 1 squared, and then he'll have u to the 4th minus sigma to the 4th. And here I have to make a couple of comments. This is biased. Oh, sorry, unbiased, gosh, unbiased. And you might add, this is the one we like. You're going to find out the variance of the variance really isn't useful in terms of a direct calculation, but it gives you an idea about how much confidence you can have in the variance. Because if the variance is varying all over the place, sample to sample, it doesn't mean much. But if it doesn't vary much, it's when it becomes important. So anyway, now we take a look at these two things, and this is unbiased, that's biased. I want to tell you one other thing. You know, people wonder, well, how come before it was just n over n minus 1? Remember, that's the expected value. Remember, for that, a variance is going to be related to the square of that. So this is, in order to go ahead and do this correctly, remember, this over here is going to have an n downstairs. We need to get rid of it. We multiply by n, but we're going to have to actually take that n over n minus 1 term and square it, and then do the multiplication, which will leave an n on top and an n minus 1 squared on the bottom. Just try to follow me on this one. That's the reason it's not just weighted by n over n minus 1. It's n over n minus 1 quantity squared, and there'll still be an n on top at the end of the day. So that's it, and u to the 4th, this one you have to know, is the 4th central moment. And a lot, I mean, it's so far probably seems too abstract to really appreciate how to apply this to problems. And what we'd like to do, ultimately, is do kind of the inverse. If we have an estimate of the sample and we have the variance of the sample and then the variance of the variance, if the variance of the variance is small, then we can infer the true mean and true standard deviation, or true variance of the entire population. That's the idea, and that's what polling is all about, by the way. And how much confidence you get into a poll, we'll talk about in a bit. So now, after saying all that, there are two distributions he uses all the time for these type of problems, and they're very common in the real world. One is the Gaussian. Almost everything, and this is called the central limit theorem that I haven't done a lot of work with, but it says anytime you have a large number of things you're sampling, even though, say, you're sampling from sets that are all over the United States. It could be populations and just health figures, something like that. It doesn't matter what it is. If you take a large enough sample, the statistics involved will become Gaussian. It's called the central limit theorem. Have you heard of this in any other classes? When you get into, some of you are going to be process engineers, probably. You work at Intel and places like this. Process engineers have to know statistics and how to apply them and random probability theory to all sorts of processes, and the Gaussian distribution is their savior, because that tells you so much. So in the bottom line is, when you have a Gaussian distribution, now you don't need to write this down, this is just to remind you, in general, a Gaussian distribution of any variable is going to be equal to 1 over the square root of 2 pi, and then this is the standard deviation of that sampling set. Then it's going to have the exponential variation here, and it'll be a minus x minus the mean value squared over 2 sigma squared. And that's for all values of x. That's generally true. If that is the case, then if you want the, I'll call it nth moment. So the expected value of x minus x bar to the nth power, it'll always be 0 for n odd, and I think everybody knows this. You'll need to know this. But it'll also be equal to the expected value of this will be equal to 1 times 3 times, and it really is going to be n minus 1 to the sigma n here, which means you can get it. You can get the central moments for all these. You all with me, class? If it's odd, it's great. If it's even, that's what it is. Now, the reason I'm saying this, the one you look at is the fourth central moment. So if we're talking about a Gaussian distribution, this would be the fourth central moment. That's just going to be equal to 3 times sigma to the fourth. Can you all see that? You all with me on this? How many knew that, by the way? You remember that formula? That's an important one to know. That's for a Gaussian distribution. The other one that comes into play commonly, and the reason is it has to do with phase angles. Now, if you think about, any kind of sinusoid or cosinusoidally varying wave that you're sampling, just randomly sampling, the phase angle in that argument, if you just forget about omega t, if you take a look at cosine of theta, and theta is varying continually, and you're sampling just randomly, well, that phase angle itself will be uniformly distributed. You don't, honestly, I don't think I can prove it right now, but there's a proof on this, that it really becomes something where if you have a uniform distribution, and the way they do it is this. They're going to say that I'll have something that goes over the range of delta x here, and the height of this will have to be 1 over delta x, and this would be f of x. So if that is, in fact, what your density function looks like, then if you remember, there's a formula in your book on this, but you remember that the actual standard deviation of this, and I'll put it up here, so for a uniform distribution, the second central moment, or sigma squared, is equal to 1/12 times delta x squared. Do you remember me doing something like this before? Do you remember that? And I'll give you the general formula, because we want the fourth central moment. I would give this to you, by the way. You don't have to know this for the general form. I'm trying to find where this is. Flip back a few pages. If you look in your book, it's in Denny's notes, but I don't know if it's clearly shown in the book or in the notes, the actual book's PDF. I'll show this to you once I find it. There it is. I'm going to write this down. This one I'll give you. In general, for a uniform distribution, I want to make sure I get this right. The expected value of x minus x bar to the nth power will be equal to 0 as usual for n odd. And will be equal to, the way I'm going to have it down here, it's the way Denny's notes have it, delta x to the nth power over, and here it's going to be n plus 1 times 2 to the n. And that would be n even. I'll get out of your way in a second. Don't bother trying to prove all these things. You can, it's easy proof, it's not hard to prove just for the sigma squared, the second central moment. But when you get up to the fourth and higher moments, the integrations get a little tedious. So I'm just telling you, it gets irritating. And the reason, and what I've done too, is I've centered it about 0. This would be delta x over 2. And this would be minus delta x over 2. So, I mean, basically we don't need the mean. We can just look at that. The mean is 0. Take care. Okay, so now what does that mean for the fourth central moment? The reason I'm talking so much about the fourth central moment, these formulas need that. That's the reason. Can you all see this, class? Right here, u to the fourth, e. That's the one we care about, not the fifth central moment or the third. So for this one, the fourth central moment, will be equal to whatever the spread is to the fourth power over 5, and this would be 2 to the fourth, which is 16. So it would be that, and if you think about that, well, it depends what delta x is, but that's 16 times 5. So I guess you could use 80 in there, but that's the formula. We're going to do problems, and I want you to see this applied. Here's what I'm going for. I'm going to be using this formula and this formula to get the variance of the variance. Everybody follow me? And we might just calculate the actual variance of the sample too, but that's more or less it. We can get that directly. So now, going back to where I was starting. A lot of these. Let's do example, not problem, example 4-3.1 for starters, and I'm going to do it over here. I'll leave those formulas up. The PDFs are great, but I'm not going to just put up PDFs in this class. Frankly, I think working problems is the way you're going to see this and retain it. I'll ask questions to see how much you do retain. I should have left that formula up, but that's okay. Okay, for this one, example 4-3.1, I believe. Okay, go ahead.
This is for the random waveform of figure 4-1.
Okay, here's what he's talking about. There's a waveform earlier on that's always referenced, and that waveform has this. It has a standard, if you're looking at 4-1, you'll see it. I put it in my book. There's a standard deviation of 9 and a mean value of that, I believe, of 10. Can you confirm that? You see it? I wrote it in that book, and if you got the PDFs, can you guys edit a PDF? I think you can, actually. You can, do you have Adobe Acrobat? If you do that, you can bring it in, you can make notations in the I make that all the time with PDF stuff. I also write in my book all the time. All right, you ready on this one? So that's the information we're given. Now keep going.
Find the sample size that would be required to estimate the true variance of the waveform.
All right, hold on. We want n, and we want the true variance of the waveform, right? So it's unbiased. Let me just write this down. So I'll put the tilde squared, and that is what? It is actually equal to. Well, go ahead. Before I go.
Let's see. Estimate the true variance of the waveform with a variance of 1% of the true variance if an unbiased estimator is used.
All right, so basically it's this. The variance of this, right? And if you think about it, unbiased, correct? Do you hear that word? Unbiased, so I go immediately to n over n minus 1 squared, and then we have to get u to the fourth minus sigma to the fourth. That's not the fourth central moment, that's the actual variance squared, or the standard deviation to the fourth power. Follow me on that, class? We're using that, and what did you see say this is? He's saying, let me just write this down. The unbiased variance of sigma tilde squared bar is what? What was that?
Variance of 1% of the true variance.
So the variance of the variance is 1% of the true variance? Is that right?
I believe so.
Yeah, all right. So 1% would be 10 to the minus 2 sigma squared. Follow me? That would be 1% of the true variance. Do y'all follow me on this, class? By the way, he likes to use standard deviation and variance almost interchangeably. Standard deviation would be the square root of that. Square root of variance. With me? Okay, so now we come over here, and I can equate that to 10 to the minus 2 sigma squared. We want to know the value of n that would make this happen. I'm defining the mathematics now based on the problem statement. This is unbiased, the variance of the variance. This is what he said it equals. So now, I come down here and I want n. I want to show you something. It's Gaussian, right? Remember, for a Gaussian process, that when we take a look at the fourth central moment, that's equal to 1 times 3 times sigma to the fourth. Can you follow me on this, class? Y'all know what I got? How many know where I got that? I just put up that formula, right? That's by definition. So I can come down here, I'm going to modify this thing. And what I'll do is do it right here. So I have basically n over n minus 1. If you have calculators, I'm going to ask you to do this. And now my u to the fourth right there becomes 3 sigma to the fourth minus sigma to the fourth equal to 10 to the minus 2 sigma, or wait a second. That should be to the fourth. Can you read that problem statement again?
Find the sample size that would be required to estimate the true variance of the waveform with a variance of 1% of the true variance if an unbiased estimator is used.
So it's 1% of the true variance. We can do it this way, but somehow I think that should be squared, but I'm going to leave it at this. Follow? We're going to see what happens. So let's just see what happens. That means I have n over n minus 1 squared. Here I have 2 sigma to the fourth would be equal to 10 to the minus 2 sigma squared. Do you agree with that so far? I'll simplify it. What I'm going to do at this point, I'll divide both sides by sigma squared. That means this is sigma squared. And then I'll divide both sides by 10 to the minus 2. So that's going to be divided by 10 to the minus 2, and I have this. Y'all follow me? I know you have to write another line in your notes, but I'm doing the math right here. It's just a reasonable way to go about this. Now, what I'm going to do is multiply both sides by n minus 1 squared, and then square it out so I get this. I get n squared minus 2n plus 1. I'll give you a second. Did y'all follow me what I'm doing? I hope you can see what I'm doing. I'm not trying to, go too quick. I'm just trying to show you. You can manipulate this however you want. Ultimately, we got to solve for n. Now, this number right here is the thing I'm gonna be sure to calculate right. So sigma squared, right there is 9, correct? By definition. So I have 2 times 9 over, and this is going to be 10 to the minus 2, so it's really 200 times 9, right, or 1800, I think, right? Agree, class? That's equal to n squared minus 2n plus 1. Now I use a quadratic. Keep your calculators out. Make sure you know how to use your calculators for quadratic solutions. And I get n squared minus, and this is going to be 1802n plus 1. And that means n is equal to minus b plus or minus square root of b squared minus 4ac over 2a, and here a is 1, b is 1802, I'll get out of your way in a second, and c equals 1. 1802, pardon. You agree with that, class? You know how to do quadratics, right? Just to make sure, this is something you have to know. If you have any equation, ax squared plus bx plus c equals 0, and you want the roots to this, it would be x equals minus b plus or minus the square root of b squared minus 4ac over 2a. There's 2 roots possible. Plus or minus the square root, right? What do you get for this value?
Pretty much
1802, and what's the other one? 0. 0 is not allowed. Follow me, class? Okay, so if you take a look at, the sample size is 0, think about it, it's rational. Makes no sense. All right, the answer for that one, I think that's right. All right, now that's unbiased, right?
Yes. The next one just asks for the same thing, but biased.
All right, now for the bias, what's the one difference? Here, instead of using this, we use u to the 4th. We can do this. Why not do it just to show you? All with me? This is the equation we're going to use. I'm going to put it over here. Did you get 1802 or 18 like in a fractional or a decimal point after that? Or did you get right on the button?
It's like 1801.999.
Yeah. The funny thing is round up. That's what I should say to everybody. Okay. The next thing we have is the bias. So we have the variance of s tilde squared equals u to the 4th minus sigma to the 4th. And here it's over n. We want n here. This is an easier one. So when I have u to the 4th, that's still going to be 3 sigma to the 4th minus sigma to the 4th over n is equal to, just like I had here, 10 to the minus 2 sigma squared. I'm going to stop there. Does everybody see that's the bias estimate? How we would restate this problem? Or I'd say solve for the value if an unbiased, or I mean a biased estimate was used of the variance. Variance of the variance, pardon. Correct? And to simplify, what do you notice? N equals, well, this part is going to be 2 sigma to the 4th, right? I multiply both sides by n and divide by this, and then I have to divide it by 10 to the minus 2 sigma squared, and that's going to be what? 2 sigma, so it's really going to be 200 sigma squared, sigma's not, so that's 1800, isn't it? Or no, is it 1800?
That's right.
Yeah, what does he have?
1801.
I don't know about that. That looks like 1800 to me. So I don't know how he got 1801. It can't be anything else. I mean, the math there is solid, right? Just make a notation of that. All right. I want to apply this stuff. The real trick on this one is taking the wording of the problem and making it make it work with either the biased or unbiased formula, preferably unbiased for anything. Or that should work. All right, now in the problems, let's see, get down right in the notes. What I want to do are some of the problems in the back. And the first one in this section, which is 4-3.1, I skip. He gives a whole bunch of numbers. He gives like 10 numbers. And he wants you to calculate the standard deviation for that, which means you have to type in all these. I'm never going to give you a problem. I mean, I gave it for homework, like a MATLAB thing, you should be able to download or in some way, shape, or form access information about the sample values online. And then you can write a little routine to calculate the standard deviation in the fourth central moment. You with me, class? I'm not going to ask that on a quiz or test, which you're most interested in. But the next parts I will ask, and that means be familiar with Gaussian and any kind of distribution that's constant in terms of probability density function, invariant. All right, it's like for that flat, basically. Density function doesn't vary. So let me go to the 4-3.2. And go ahead.
4-3.2. A zero mean Gaussian random Tom function is sampled so as
Gaussian random what function?
Tom function
Okay.
is sampled so as to obtain independent sample values. How many sample values are required to obtain an unbiased estimate of the variance of the Tom function with a standard deviation that is 2% of the true variance?
So he's saying the square root of the variance of this true variance, right, is equal to what? What was the standard deviation?
It's just saying 2% of the true variance.
Of the true variance?
Yeah.
Okay. All right, so that's 2 times 10 to the minus 2 of sigma squared true variance, right? Okay. That's unbiased. So I'm just going to put it down here. And actually, since it's, he doesn't say, didn't you say something about a standard deviation? Did I mishear you?
Yeah, he said, how many sample values are required to obtain an estimate of the variance of the Tom function with a standard deviation that is 2% of the true variance? He never gave a value.
So this is actually the square root of this. That's what he said. You're going to have to read this carefully and translate. So he's not giving you the variance of the variance, he's giving you the standard deviation of the variance, which is that. Okay? Just keep that in mind. So now put down, this is unbiased, so the variance of, and this is unbiased. Do you remember what it is, class? Anybody? Well, we've got it written down, but what is it? N over n minus 1 squared, and then here's, it's always going to be the fourth central moment minus sigma to the fourth. It's Gaussian. The whole idea is, in the earlier part of that problem, he's talking about the samples are statistically independent, and if you get that kind of a statement in a problem, it means you're sampling things that have nothing to do with a prior sample. They're not related to any kind of a known distribution. It becomes Gaussian. Central limit theorem says it will be. So for that, it's equal to, I'd have to square both sides, and I'm going to do it right here. So this is going to be 2 times 10 to the minus 2 sigma squared. Do you follow me? Whenever you see that word standard deviation, think it's going to usually be the square root of the variance that we're dealing with. That's how he's defining it. We'll find out in a second. You with me, class? All right. Now translate this into more numbers. So I'm just going to leave it as n over n minus 1. These numbers can get huge, by the way. You've got to be careful sometimes. What is u to the fourth for a Gaussian fourth central moment?
3 sigma.
It's what?
3 sigma to the 4th.
That's right. 3 sigma to the fourth, and it's going to be minus sigma to the fourth, which is nice, is equal to, and this is going to be what? 4 times 10 to the minus fourth sigma to the fourth. Now I'm putting it down like this so everybody can see this. This is the equation we're solving. Everybody agree with this, class? My point here for doing that, you see how sigma to the fourth goes away? Because a natural thing that happens on a quiz or test, if you're a little nervous, is we don't have any information about the value of sigma squared, sigma to the fourth, or anything like that. Follow me? You don't need it, because you can all see it cancels on both sides. Can you see that? All right, so this becomes simply 2 sigma to the fourth. And now you can see you can get rid of sigma to the fourth on both sides. Remember that when you're doing these problems. Look for cancellation if something isn't stated explicitly. It almost always happens. So this goes away, this goes away. And if I gave it to you here, just like that, what would you find for n? I say this because this is where, believe it or not, on quizzes and tests, mistakes are made at this level. Sometimes the problem's formulated correctly, but you can't solve equations like that accurately all the time. You should be able to. So, I mean, I don't know how you do this, but generally speaking, I'm going to multiply. First, I'm going to divide by 4 times 10 to the minus 4th. And I get this. And that's 1 over there. Then I multiply by n minus 1 squared and square it out. So I get n squared minus 2n plus 1. It's always going to be that kind of a form. Are you with me? Now, if you look at this, the one thing that's going to change is the coefficient of n. Not n squared and not the 1. So here, I really have, if you look at this, I have n times, and it's going to be 1 over 10 to the minus 4th is 10,000, and that's 1/2 of 10,000, or 5,000, right? Would be equal to n squared minus 2n plus 1, or it really is 0, is equal to n squared minus 5,002n plus 1, and then if you get into that solution, it means n equals, if you take a look at this, minus b, which is going to be plus 5,002, plus or minus the square root of b squared, 5,002 squared, plus, or, sorry, it's going to be equal to minus 4 times a times c, or minus 4 over 2. And yeah, it's got to be about 5,002. I kind of remember doing this problem, but I don't remember. Is it 5,002? Is that the answer, by the way? Y'all follow me on this? So what I did last night when I was doing a whole bunch of different kind of problems, I set up this kind of a quadratic right here. And the only thing I changed, see, A is going to be 1, C is 1. So I know for this one that 4 stays, the 2 stays. And the only thing that happens is this value is going to change depending on what comes there. And the problem is these get bigger and bigger. Well, it gets closer and closer to that value B. If B is like 100 or something like this, it's off a little, but it's close to that. Y'all with me on this problem? That's Gaussian. Let's do another one. Let me erase this. So 4-3.3. Were these assigned, by the way, on OneNote? Yes? Okay, how many tried them, just honestly? Nobody? Okay, I'm glad I'm doing this. I was gonna just jump, if a bunch of you did, I'll jump to the next section. Go ahead.
It is desired to estimate the variance of a random phase angle that is uniformly distributed over a range of 2 pi. Find the number of independent samples that are required to estimate this variance with a standard deviation that is 5% of the true variance, if an unbiased estimate was used.
Okay, so let me just go here and I'm gonna put n, now we're back to the n minus this thing, u to the fourth minus sigma to the fourth. And here we have a phase angle, right? So really, we're talking about a phase angle, an f of theta, and it's uniformly distributed over from minus pi to pi, right? It's over a total range of 2 pi, isn't it?
Yes.
So he has a span of 2 pi, and the height of this is going to be 2 pi, and that's the density function. I'm just showing you this versus, you don't have to write this down, but it's constant, right? Now, what we need is the fourth central moment of that. You always, I mean, this is one, we're going to need that right here, and we need the standard deviation. The standard deviation of this is just going to be 1/12, and then it's going to be 2 pi squared. What does that come out to? So it's 4 over 12. So it's pi squared over 3. Do you all agree with that? That's the standard. Now I know that 1/12 business, that form. It's delta x squared over 1 over 12. Now I need the fourth central moment of this. Now this is a constant one. As I recall, the formula had n plus 1 times 2 to the n here, and then it's going to be the delta x spread to the fourth power. If you don't remember it, don't worry. I'll state what the fourth central moment is for a constant, for a density function, it's constant, or a uniform density. You all follow me, class? All right, so for this one, I forgot what this is. This is going to be 2 pi to the fourth power over, and this is 5, well, this is a crazy one, over 2 to the fourth, or 16. Now this is going to be fun. So I have basically 2 to the fourth, pi to the fourth, over 5, and this is going to be equal to 2 to the fourth. So it's pi to the fourth over 5 would be u to the fourth. And what did you say he wanted this equated to?
He's looking for how many sample values are required to obtain the estimate.
Up to what accuracy?
Let's see.
I think it's 5% of the variance.
Yeah, 5% of the true variance.
5% of the true variance? So this is going to be equal to 5 times 10 to the minus 2. True variance is, I'll just put sigma, or sigma, sorry, sigma squared. Just leave it like that. And now I'm going to start modifying. Y'all with me, class?
I think that's all squared too, because it's
What?
It's the standard deviation is 5% of the true variance.
Oh, we got to square it.
Yes.
So I need to square this thing. Are y'all with me, class? Standard deviation always means you got to square it to equate it to the variance. Always. With me? Okay. Back to this thing. So now I'm going to take n over n minus 1 squared. Now u to the fourth is pi to the fourth over 5, right? is sigma to the fourth, so sigma squared is pi squared over 3. So that's going to be minus pi to the fourth over 9 equal to, and this is really going to be 5 times 10 to the minus 2 squared sigma to the fourth. And sigma to the fourth, of course, is going to be pi to the fourth over 9. I'm doing it this way for a reason. Take a look at that. Make sure you understand how I got each term down here before you continue. There's something I bet you see by now that I'm going to do. Anybody want to take a guess at what I'm going to do next? There's something we can get rid of. Something you eat occasionally. Pi, right? You all see, get rid of that pi to the fourth. Don't leave it there. It only irritates you on both sides. Follow me, class? I want to make sure you see it. Just get rid of it. I'm trying to show you something I realized some time ago, but anytime you can simplify equations, especially when you have numbers like 10 to the minus 8 to the 5th power, on both sides, get rid of them. They do you no good in the calculation except cause errors. I get down to that point, and from here on, you can multiply both sides by 45. Do you all see that? If you multiply this by 45, well, you don't have to do it this way. What we can do is get a common denominator, right? 5 times 9 is 45, right? I would have 9 minus 5 over 45. I'm just doing it this way. So that's going to be 4 over 45 on this side, and then over here, that's 5 over 45. You can see where I'm going with this. I'm trying to make my life easy. You agree with that, class? What might be my next step since I'm lazy? I don't like doing more than I need. Can I multiply 45 on both sides and get rid of that too? I mean, you solve it any way you want. I want to see what you guys get on your own. So I get 4 and 5 there times that. So finally, let's see. I have n, bless you, times 4 over 5 times 5 times 10 to the minus 2 squared equal to n squared minus 2n plus 1. You know what I'm up to? Now I simply get everything equal to 0, so I get 0 equals n squared, and then it's going to be minus the quantity 2 plus whatever this comes out to be, 4 over 5 times 10 to the minus 2, squaring it, n, I should say n outside here, n plus 1, and therefore b is equal to 2 plus, or it's actually minus 2 plus 4 over 5, what is that, 25 times 10 to the minus 4th, and a c equal 1. And what do you get for the value of n here?
322.
What is it?
322.
What's the answer?
322.
Anybody else get that? It looks easy to do, but these calculations get messy, and I'm warning you about one thing. If you start doing the pi to the fourth stuff and just trying to keep all that on track, you're probably going to make a mistake in time. Just care, yeah.
This might be a dumb question, but how do you know when you're supposed to use the biased versus unbiased equation? It says it explicitly.
It's explicit.
Okay.
If they don't tell you, you always go with unbiased.
Okay.
Always. Basically, he's contrasting. He's showing you how large values of n, biased or unbiased, give about the same answer. I mean, they literally overlap at a certain point. So he's just trying to show you when n is small, 40, 30, stuff like this, then unbiased becomes very important.
Thank you.
And let's see. Those are the ones I wanted to do. The next one I think is they give you a Gaussian or they give you an exponential distribution, isn't that right? If you look at 4-3.4, just help.
U to f x e to the negative x.
Uh,
F of x is equal to e to the negative x.
Yeah, but u of x times that, right? Isn't there a u of x that's only positive x? You made a mistake. It's supposed to be, if it's not just for positive values, the
I mean, it
density.
states that x must
Positive?
be greater than 0.
Okay, all right. And what does he ask for?
How many samples are required to estimate the variance of this time function with a standard deviation that's 5% of the true value?
All right, I didn't do this one. Let's try this. I want to see how you guys do, all right? I'm just curious to see how much you retain. And then I'll move on to the next stuff. So, does he say unbiased in there?
Yes.
Okay, which is my favorite. So for this one, now there's one thing about this that should trigger you. You'll notice, this is not Gaussian or constant. It's not a Gaussian distribution, and it's not a uniform distribution. It's something else. Which means the force central moment isn't given. So now we're going to find out how we get there. Actually, your calculators probably can do this thing in a trivial way, I think. So here, for 4-3.4, he gives you f of x is equal to e to the minus x. I'm going to put u of x here. And now he says he wants to know how many samples you need to take. So you get the variance. Does he say unbiased in there, by the way?
He does.
Okay. I'll just put it up. The variance of s squared bar is equal to n over n minus 1 squared u to the 4th minus sigma to the 4th is going to be what we're after. And he says, give me the how close or the accuracy level?
With a standard deviation.
Oh, stop. Standard deviation means I'm going to square the next thing that comes. Go ahead.
That is 5% of the true value. I'm guessing that's the true
10
value
to-
of the variance.
Yeah. 10 to the minus 2 times sigma squared, and this is going to be squared. Y'all follow me, class? Okay. Now, the key on this one where people make mistakes, if you went for Gaussian, this would be 3 times sigma to the 4th. If you went for the constant value, I think I erased it, over there, it's going to be, what is it? 1/5 of the actual standard deviation, or sorry, the variance squared. I'm not going to say too much more about that, but in other words, you would know how to deal with either a constant or uniform distribution or a Gaussian, but this isn't either. Y'all with me? So how are you going to do this problem if it's on a test? All right, I got that. Now, if I wanted the standard deviation, first of all, the variance, how do you get that? How would you get it? I'm asking a very good question. I can see this on the final.
Just need mean squared value minus the.
What do you need for this? Well, we'd like the mean value, right? Right? We'd like the mean, and then we like the mean squared value, right? If we have those two, we could get the standard deviation to be equal to the mean squared value minus x bar squared. Do y'all follow me on that? All right, so where do we start? How would you get the mean value? You have calculators. If you didn't have calculators, it'd be a little different story. You can multiply that density by x and just do the integration. Anybody want to make a statement as how else you could do it based on 2 lectures ago? Laplace transform, right? If I took the Laplace transform of that, it would become, and I'll put this, fx of s is going to be equal to 1 over s plus 1, right? Correct, class? Then, if I take a look at this, if I take the derivative of f of x of s with respect to s, now I get what? Minus 1 over s plus 1 squared. And to get the mean, because it's odd, I'd have to multiply by a minus sign and evaluate this at s equals 0, right? And that would be 1. You all agree with that? So I got mean value. How would you get the mean squared value? Now again, with your calculators, you can just write what? X squared times e to the minus ax and integrate. Do you agree? I'm curious what your calculator's good for that. Or what could you do? Put that as a negative, take another derivative of that, right? If we take another derivative, what do we get? Well, this is really equal to s plus 1 to the minus 2. That's the way I like to write this. So that would be the first derivative. There would be a negative sign, right? In other words, this would be the first derivative of f of x of s with respect to s. Now, if we took another derivative, what happens? I'm making a point here. It's easy to do this, but it's easy to make a mistake. Now we take out, the minus 2 comes out in front, so I get a plus 2 over s plus 1 cubed. Do you agree with that? And we have to evaluate that. Now we don't multiply by minus. So this would be equal to the second derivative of fx of s with respect to s squared. Evaluate that at s equals 0, and it becomes 2, doesn't it? Can you do that in your calculator? I'm very curious if you get exactly 2. You should. I didn't actually. Did you get?
I got both. I got 1 and 2.
All right. It's easy to do it this way, in my opinion. The problem is, for higher order, the fourth moment, for instance, not central moment, the fourth moment, now you got to keep taking derivatives 2 more times. Do y'all follow me? And it can get irritating. This one's not bad because it's just a 1 in there, plus 1, but if you had something just plus a, then you could get something like a to the 4th, and a may be 100 or something like that, or 199, something like that, and it can be a problem just doing it in your head, so you can use your calculators. Anyway, back to this thing. So we've got the mean value and the mean squared value. So what is this going to be? The mean squared value is 2, right? Minus the mean value is 1 squared is 1, so that's 1. Do you agree? All right, now, I'm curious about this. How would you guys get the fourth central moment? This is something I'm asking because you all have calculators, so this would be a fair question on a final. You'd have to know how to use it. Anyone? Remember, this formula says fourth central moment, doesn't it? What is that equal to? Mathematically speaking, u to the 4th would be equal to an integral over the range from 0 to infinity. I think your calculators have a symbol for infinity you can insert in an integration. And now you would take x minus, and the mean value is 1, right? To the 4th power times e to the minus x dx. Now I'll tell you, if you want to take that and square it first, so x minus 1 squared is x squared minus 2x plus 1, and then multiply that by x squared minus 2x plus 1, you can do it and you can get a bunch of terms. Or I think your calculator might be able to do that, but I don't know. Give it a shot. I want to see. I'm very curious about this. And I'd suggest you know how to do this because you're probably going to see a problem like this on your final. Not on the next quiz, but on the final for sure. This is where I assume you know what you're doing with your calculator. And that assumption's not always valid. Some people, I mean, literally, hardly ever use your calculator for any kind of symbolic integration or everything, things like this, and then they have, or I should say actual integration, they are clueless as to what to do with it. This is it really that bad?
I got 9.
That's what I got.
What did you get?
9.
Anybody else confirm that? You got 9 too, Elijah?
Yes.
You got it too? All right, I'm gonna go with 9. All right, now let's see what happens. Did you not get 9?
Mine can't do that much. ELEC overflows.
I was worried about that. What kind?
TI 36X Pro.
Anybody have a 36S Pro that can do it? That concerns me.
I'll just do it by hand, it's okay.
There's another trick to do it, and I'm just gonna say this, I'm not gonna do it right now. We can take 2 more derivatives, right? You can get the fourth moment, right? If you got that and you want the 4th central moment, you can go back to the definition here, square the thing out. Now the odd integration, well, I shouldn't say this because it's not over the negative range, but you can manipulate from there. It's not gonna be easy though. 4 central moments are never easy in general. Anyway, back to this thing. If we have that, and I'm gonna just plug in here, okay? So we know that this is 1. Agreed? So I get rid of it. And if that's 1 squared, the variance squared is what that is, that's 1. Agreed? U to the 4th you said was 9. Who said that? You guys all said it, right? So I can put a 9 in here. You see how I'm doing this? And now we should be able to solve this. At least, let's see if we get the answer they get. I don't know if we're gonna, but I'm gonna try. So I have 9 minus 1 is 8, and that means I have 8n, and then I have to take that and divide it by 5 times 10 to the minus 2, and I have to square that, and that would be equal to n squared minus 2n plus 1. That means 0 is going to be equal to n squared minus 2 plus 8 over 5 times 10 to the minus 2 squared n plus 1. And here n equals, remember b is going to have, what is it going to be? I got 8 over 25 times 10,000.
3,202.
What is it?
3,202.
Anybody else confirm that?
I got that.
Pardon me?
I got that too.
3,200. Sorry.
Hold it. What'd you say?
It's 3,200.
3,200.
And
Is that all right, class? 3,200?
And 2.
And 2. Sorry. And 2. What's the answer?
I don't see it in here.
Oh, they didn't do this one?
It doesn't.
Now, the reason I'm doing this is it isn't in there. Okay, well, now write it down. I would know, because this is an irritating one. These are the kind of things that used to irritate me as a student when you had to use, I'd say it's outside the main theme of the class, but you'd have to figure out how to do something with either Laplace transforms or Fourier transforms, something, to get values. In other words, the professors used to do this all the time to me in undergrad. They'd make sure you knew circuits, knew signals and systems, all that, because they're assuming you know it well because you're going to use it all the time. And they'd always make sure they worked it into their lectures. It used to irritate me until I figured out that's exactly what's going to happen all the time in my classes. Okay, with this one, I think it's 11 o'clock. Now let me tell you where I'm going with this, because we have, what, 5 lectures left, basically? All right. Now I need to recover my text. And, yeah, I put a copy of this up for everyone. I always thought the solution manuals, at least one of my courses in undergrad, they would sell you the book, and they'd say the solutions manual when we went to the bookstore, because they knew how important it was to be studied. And I don't know if it's still done that way, but you can get the solutions manual for almost anything. I want to tell you where we're going. The next section is about student T distribution. I want to tell you, there's some interesting stories in this section. Do you know what Guinness beer is?
Mm-hmm.
Guinness Stout? Well, the guy that came up with this is actually a statistician for Guinness. He's a guy that figured out how to sample the vats of beer to figure out different things. And more or less, I don't know how alcohol and stuff like this, get statistical information about that. But it also works with grade distributions. However, it's not that important in the overall sense. I may cover that, but what I'm really going to cover is going to be in chapter 5, random processes. And I just want to tell you this. In chapter 5, we talk about stationary and non-stationary signals. I'm going to give you some assignments. I may do chapter 5 enough if I have time to do student. It's interesting, but it's not essential. And they talk about ergodic and non-ergodic. Now, the term I just want to mention right now and ask you if you've heard. Have you heard of wide sense stationary signals? All right, let me just tell you what it means. If you've heard of noise, white noise, you've heard of all these things that are associated with basically like shot noise, thermal noise, with trend. You probably heard about it in your microelectronics class, in digital electronics, how many have? Who cares? Before I just start talking. All right, well, if you have heard about that, that is called a noise that is based on natural phenomena, and it's wide sense stationary. The noise itself has a very well-known statistical distribution, and every single thing that happens in the future is not in any way, shape, or form based on what happens in the past. It is completely independent of that. Natural phenomena like how, and now, things that man creates most of the time are not that. Most of the time, previous values dictate future values, and that's the problem with a lot of that stuff. So I'm going to get into this, and they're called ergodic and non-ergodic. And have you heard of correlation in here? How many have? In your own words, what's correlation? In simple sense.
They're related but not caused by one another, necessarily.
If one happens, there's a likelihood that something else will or won't happen, that gives you more information about a future event. Follow me? It's called correlation. Well, we can correlate value, functional things, and you'll see this. And then we can take the Fourier transform of that, and this is where it's really important. We get something called the power spectral density or the energy spectral density, where this becomes critical as an information theory. You guys are going to have Dr. Tugnate for communications. This is the underpinning of so much of the theory in here. So that's the reason I'm going to focus on covering that. You're going to see this stuff becomes very applicable. It's not that confusing, but there are some irritating facts about it, and I'll get to this next time. Because honestly, when they talk about ergodic and non-ergodic processes, it's really, are they wide sense stationary or not? And frankly, there's no way you guys could appreciate I don't think you can appreciate the mathematical complexity of the exact definition. It's not easy, it's something that has to do with a lot of stuff. I think Albert Einstein, I could be wrong, but I think he got a Nobel Prize for this in Brownian motion. So, I mean, he didn't get a Nobel. He should. Einstein did 4 things, all of which someone received a Nobel Prize for. He only received it for, do you know what it was? Einstein won total electric. Probably the most minor contribution. He did general relativity. I mean, that was the most amazing thing probably in modern physics ever found. Anyway, Einstein was never really appreciated the life